Okay, so the next talk is Holbert, Reading, Writing, and Improving in the Browser by Liam O'Connor and Rihanna Ajad. And Liam will be giving the talk.
Right, thank you, Jonathan. So today I'm going to be talking about some work that I've been doing with a few undergraduates. Particularly Rihanna did many of the contributions in this work. But it's been something that I've been mulling about in my mind for a long time now. When I was at my old job at UNSW, I taught a number of courses on things like logical foundations, programming language semantics, and so on. And in recent years, there's been a few new textbooks that have come out that have tried to integrate a proof assistant with these courses in a very deep way. So all of the exercises, all of the mathematical reasoning that the students do is conducted inside a proof assistant. These courses have been quite successful. Most notably the Software Foundations course, which uses the COP proof assistant, and also like there's other books like Concrete Semantics for Isabel, but also PLFA, which we use at Edinburgh with Agda, but it doesn't have a cover, so we don't have an image there for you. But all of these tools, all of these books rather, use mature proof assistants that are designed for more general purpose use. They're not designed specifically for these educational use cases. So these tools are quite complicated. They have a lot of features. They're designed to make lots of large-scale reasoning. A whole compiler was verified in Coq, and a whole microkernel was verified in Isabel. So that's a lot of infrastructure that you need to support that kind of industrial scale proof. And that's sort of not what you want when you're using it in an educational context. In particular, students will always have problems installing the damn tool on their computer, and I don't want to have to think about that ever. Once the students get it working on their computer, they have to learn sometimes very complicated syntax. Isabel in particular has a few different languages that are sort of all mixed together in its proof script, which can take quite a while to get familiar with and get used to. The syntax is quite unconventional. But most of all, these books are sort of taking me back to the experience of learning programming in the days where you'd have to get a book to learn programming, and then you'd get a bunch of examples, and they'd be written in the book, and then you'd copy them into your editor, and then you'd run it through your compiler, and it wouldn't work, and then you'd wonder what's going wrong, and then maybe it's some difference between the compiler that you're using and the code that's in the book, or something like that, or maybe the book is correct, and you just copied it in wrong, and then you have to constantly context switch between the book and the code that you're writing in the editor. It's a bit better because these are digital textbooks, so you don't have to literally read paper and type it in. You can select and copy and paste, which prevents many errors, but still, there's a lot of context switching that you have to do here between the book and the theorem prover. So what I want to do is have a proof assistant with a very low barrier to entry, that they don't need to install, and that doesn't require me to, that's integrated with the book itself, so that it doesn't require me to constantly be switching between the book and the prover. So to enable this low overhead, what I want is the notation of the proof assistant. The syntax of the proof assistant should resemble the notation and the syntax that we use in pen and paper mathematical reasoning as far as possible. Now, of course, this is not in general possible. Mathematical notation is highly ambiguous and weird and idiosyncratic. But I would like to at least approximate that notation so that the unfamiliarity to students is reduced as much as possible. So if we take a look at some conventional notation, let's say for a logic course, then we might specify a propositional logic, let's say, using natural deduction, right? This is notation that's taken straight from Genson's 1935 paper, right? We have a bunch of rules here for describing logical connectors. If I can prove A and I can prove B, then I can prove A and B. If I know A and B, then I can prove A. And if I know A and B, then I can prove B, and so on. Here we have a hypothetical derivation using these little ... notations. So if, assuming A, I can derive B, then I know A implies B, and those sorts of things. So we have all of these introduction rules and elimination rules for all of our logical connectives and operators. Notably here for not, I'm using a nested meta variable quantifier. So I'm saying if, assuming P, I can derive any conclusion, that means not P is true, right? Because only false implies everything. And similarly, if I know not P and I know P, then I can derive anything, X. And then when we construct a proof using this natural deduction system, we can work bottom up. We can start by writing our conclusion that we want to show, in this case, commutativity of conjunction. And then we apply our rules, sort of like a video game. This is your inventory, and you apply this to the monster, and eventually the monster is slain, right? So we apply our implication introduction rule, and now we've introduced a new assumption, A and B, and we need to show B and A. To show that, we use AND introduction. Now we need to show B, and we need to show A, which we can do using further rules, and eventually we boil it down to our assumption A and B that we introduced earlier. So can a proof assistant just use this notation? Well, the answer is yes, and you're looking at it. I just click a few buttons here, enable the editing controls. Let me delete this proof here, and we can do it again. And I'll just pull out my sidebar here. So now we have a current goal. This is being slightly adapted for presentation purposes. So this looks a little bit different in the normal mode of this application, but this sidebar looks the same, which is why it's a little smaller. But anyway, I just hacked up the presentation mode last night, so that's why it's a little bit janky. But we have this available introduction rule here, implication introduction, so I'll apply that to my goal. And now it's introduced this new assumption, which I can see over here, A and B. And I can now apply my AND introduction rule. And now I have two goals, B and A. And now I've run out of introduction rules. We have a special handling for elimination rules that I'll talk about in a moment. But for now, I can just click this button here that says show non-introduction rules. And now I can apply whichever elimination rule I want. If I try, oh, wait a minute. I think right, so I applied the wrong elimination rule here. It's saying you need B and something. It doesn't know what the something is. So I should have used ND1. No, ND2. And now I can apply my assumption 0 here. And that's how the proof completed. Now I can do the same thing with ND1, and proof is done. So that's like a whirlwind tour of what we can do here. But there's a few options for displaying things in different ways. In particular, Genson's original notation is a little bit verbose with these big vertical hypothetical derivations. So I'll turn it into the default mode here, which just uses a little entailment symbol instead, makes it a little bit cleaner. And in particular, also, I don't like the fact in my proof trees that these assumptions are not explicitly written out in the proof tree. So I'm just going to turn that on. So now I can see it's introduced the assumption A and B here, which makes it a little clearer, a bit easier to read, in my opinion. But it's no longer the original notation from Genson's paper, but I think it's a bit nicer. Okay, so is that all I wanted to talk about on this slide? I think so. But the nice thing here is that what we've done is we've managed to accomplish basically a nice little video game interface for constructing a proof. But the proof you get out is just the same sort of tree that you would construct on pen and paper. Right? Now, how can we scale this? I should also mention that this is entirely configurable. I can change any of these rules. I could even add a rule. I didn't introduce an explicit rule for true. So let's say we can always derive true. And let's say also for false, if I can show false, then I can show anything. So now I've got myself, oops, I made a typo. Now I've got myself 2 extra rules here, and now I can use those in my proof as well. So you can edit all of this. All of this is entirely configurable. But how much? Yeah?
Is there something special about X?
I introduced it here as a metavariable. So
It could be anything.
could be.
For all x, basically.
In fact, if I rename this metavariable here, let's call it Q now. It will intelligently rename the whole thing. Yeah. Yeah.
It's not checking your rules are actually reasonable, is it?
What do you mean by reasonable?
Like, can you make it like it doesn't know what these logic means, or you're basically telling it what logic means?
When you define a bunch of axioms for your logic,
Okay,
you're
so,
saying what it means, right?
okay, so this is axiomatic then.
Yeah. Well, I mean, if this wasn't in presentation mode, it would actually say axioms here, right? But in the presentation mode, it hides those headings.
Yeah, I think that another way to ask the question is these could be inconsistent. And
Of course.
Now. Yes.
And we'll get back to that. Yeah, so, but yes, I could even say, yes, we can have another one also that says false is true. Right? Of course, you could do this, but you just shouldn't. Right? Just don't do that.
Hopefully your students know that.
Well, also, if they do that, I can see.
You can explore.
Yeah, exactly.
Explore sets of rules, and that's what deduction is about.
So if you add that, I mean, sure, it'll make your proofs very easy, but. So the terms here are actually lambda terms. So, for example, this is a lambda in Holbert. We have x px applied to 8. So there's no lambda symbol. There's just a variable name followed by a dot is a binder. And which means that we can use higher order abstract syntax, that is to use functions to, use Holbert's functions to model the variable binding in, for example, rules for quantifiers. So, for example, I have here for all introduction rule that says, if given any arbitrary x, I can prove p applied to x. Then, for all bound variable a, p is true for a. And so this takes the role of substitution that you would normally do in your pen and paper rules, right? We might write some substitution for variables. Instead, we now apply these functions, and the beta reduction gives us our substitution, right? So I can do this proof now. Here we've got this proof that says if there exists an x such that not p of x is true, then I need to show that it is not the case that for all a, p of a, right? So how should we do this? Well, actually, I remember what I forgot to do in this previous slide. I wanted to talk about elimination rules briefly. So you saw that when I applied these elimination rules here, we end up with these unknown schematic metavariables here. So it's saying, I don't know what this is. It'll have to be unified with something later on when you apply a rule. This is because when you're working with elimination rules, what you're actually doing is thinking about your assumptions. You're not thinking about the goal you're trying to show. You're thinking about what assumptions do I have? How can I eliminate them? And so rather than use Genson's original approach, which is sort of thinking backwards and constructing your proof in reverse so that you can construct all the elimination rules, instead, if you click an assumption here, Instead, if you click an assumption that you can't immediately apply, it will say, oh, well, I could use this rule to eliminate that assumption, and that would unify with your goal, right? And similarly here. So I don't need to do this sort of elaborate backwards reasoning process. Instead, I can just apply the elimination rule to the assumption rather than to my goal, right?
Is there a reason you have to tell it which assumption? It can't just guess?
Well, I think it's nicer to. You'll see what I mean in a minute.
You don't want to go into proof search, right?
Yeah. So here we have an assumption there exists an x not p of x. So I'll apply the existential elimination rule here. And what this will do is it's going to unify the first assumption, the first premise of the elimination rule, with the assumption that I've selected. Right? So it will say, okay, in this case, p in this rule is going to be not px, right? So now this has introduced an assumption here, not px, and I need to show this. I need to show that it's not the case that for all a p of a, and this is for some particular arbitrary x, right? So now if I apply, let me think, how would I prove this? Well, I think we would need this one. So I apply the for all, the negation introduction rule, which says that I need to now derive any conclusion x. You can think of x as false from for all a p of a. And now I eliminate that one. For all a, oh wait, no I don't. All right, I will use this one. So now, in order to show that I have a contradiction here, I have applied negation elimination to my assumption 1, which is the one not px, and that will require me to prove px. So that way, if I have both not px and px, that means that overall it's false. Overall, I can derive anything. So I can apply my for all statement here, and I complete the proof. Right? So it's a little bit technical to see how the variable bindings are working here, but also it might be a bit confusing that we have two things called x. So of course we can just rename this to like false or something. But this is all very pretty, I think. And so this shows that we can use higher order abstract syntax to do this binding. But of course, if our lambda terms are, if we have terms that are lambda terms, then it leads to the question, well, what if we have a non-terminating lambda term or a lambda term that reduces to its own negation? I mean, you can come up with terms like this that would be very paradoxical. But the answer to that is just as I said before with the axiom sets, just don't do that. You don't have to worry about it, right? So, of course, this sort of flies in the face of a lot of the theorem prover designers' intuitions about things. They would say, oh, this is rubbish. We need to have a tight lambda calculus here to prevent this kind of nonsense. But in my view, for the educational purpose, adding the type system to the term language here would introduce more cognitive and pedagogical overhead, and I'm trying to keep that to an absolute minimum. So in particular, if I want to teach something about type systems using this proof assistant, then it's kind of irritating if I first, before teaching about type systems, I have to teach the type system of the proof assistant to teach the type systems that I want. So I'm trying to avoid this kind of circularity. I'm trying to just keep things as straightforward as possible and as close as possible to the admittedly inconsistent computer science notation that we write up here, right? Okay. So there's a bunch of other features here. We now, thanks to the work of one of my brilliant undergraduate students, Chris Maxwell, we can do induction as well. So we have here a definition of natural numbers. This should be very straightforward for everyone, but also it will derive a bunch of rules for this. The generated names are not great, to be fair. We can improve those at some point. But the most important one here is for induction. Here it says if I have, I don't know, S, let's just call it S, which is a natural number, and I have a proposition P, or a predicate P that holds for 0, and if I have a natural number n and it holds for n, then it holds for successor of n, then overall it holds for any natural number s, right? And so this is just the conventional induction principle. We can even define like mutual induction here. So I have even and then odd. And if I take the successor of an odd number, it's even. If I take the successor of even, then it's odd. And it will, of course, generate the horrible induction principle. I'm not going to show you that too long. But now we can do a little inductive proof. So let's give that a go. I'm looking at this goal here. I want to do induction on this assumption that my natural number n is a natural number. So I'll use the induction rule here. Now I've got two cases. It's done the unification, and in the paper we have all the details on how this unification works. So because it's lambda terms, it's going to be higher order unification, which is not doesn't always give you a unifier. We use pattern unification to make this simpler, so we actually do get most general unifiers in many cases. And for all the cases where we fall outside the pattern subset, where we get the most general unifiers, we have a bunch of hacks and tricks to make this work, and all of that's in the paper. But here I need to show that 0 odd or 0 even. Well, I know that it's going to be even, so I will choose the right disjunct, and that's that side of the proof done. And now I have the inductive case. So now I have a number n, and this is a bit confusing because I've got two numbers n, so I'm going to call this one k. All right, so now I've got a number k, and it's either odd or it's even, and it's a natural number, and I need to show its successor is either odd or even. So it really depends on whether it's odd or even in the first place. So I will use the disjunction elimination rule. Now I have two cases here. If it's odd, then its successor is going to be even, so that's the right disjunct here. I use that, and now the left disjunct, that. So now that's the proof complete. Now this proof is getting a bit big. Right? It's a bit unwieldy. And typically when we write an inductive proof, we don't construct the whole proof tree just from the bottom up like we do for a deductive proof. We break it up into several cases and discharge each case separately. And Holbert was this as well. It has what's called a prose style proof. If I click this button here, now it says, you're given a natural number, and there's your assumption. Now, by induction, we now have these two cases. And show is not very informative, so I'm going to say this is the base case, by the way. And now it has some text here, so you can put in all sorts of explanations that you want. And here in my inductive case, I can change the text however I wish. And now this inductive case, well, even this tree is maybe a bit too big. We can even convert this one into a prose style proof as well. They get a bit long in the vertical sense, but they get narrower in the horizontal sense, right? So you can trade off your vertical space size with horizontal space size however you want. Cool. Right. And by the way, you can convert these back to a tree and then back to the prose, and you don't lose anything. Like, it's always easy to switch around here. We also derive these cases rules, and you may have noticed that these are using equality. We have, here if I have a natural number, then either it is equal to 0 or it's equal to the successor of some other natural number, right? And these rules are useful for proving all sorts of things. But I haven't talked about equality yet, so I suppose I should. So we have equality as well. This was the work of Rihanna mostly. And in this, here I've just written two axioms for defining addition on natural numbers. So 0 plus n is n, and if I have the successor of m plus n, then that's the successor of m plus n, right? So to prove the right identity of addition here, I have a goal to show n plus 0 is n, and I know that n here is a natural number. We're going to have to do induction on the natural number. So we've got the two cases. I'll use the prose style proof here. In the case where 0 plus 0 equals 0, well, this is just an instance of the plus b rule here. So I can complete that side. And that's a bit long, so I'll just condense that a bit. OK. And now I have, assuming n plus 0 is n for some n. And this is once again another n. So let's call this one k. OK. I've got k plus 0 is k, and I know k is a natural number. And now I need to show successor of k plus 0 is successor of k. Well, what can I do, right? I could apply this rule here, and then I would get successor of k plus 0. But this goal is to show that it's equal to successor of k, not successor of k plus 0. So I kind of just want to rewrite my goal by an equality, and then I can continue my proof from there. So we have this facility. If I click that little equals button, I can rewrite my goal with any equality that I have in scope. So here I want to rewrite using the plus I rule. And so now my goal looks like this: s k plus 0 equals successor of k. And now I can rewrite again, this time using my assumption, k plus 0 equals k. And now I have something that looks very provable. And in fact, if I click the equals button again, it will just use built-in reflexivity of equality to complete the proof. Maybe it would look better if I did it this way. Not really. Let's go back. Okay. So one of the things that I want to support in future is a more calculational style of presenting these sorts of proofs. When you're doing chains of equality or chains of any pre-order, really, I'd like to be able to just say this equals that equals that equals that equals that, and have the reasons on the right-hand side, you know, something like that. That's in progress right now. It's just not ready yet. Yes. Okay. So that's all I really wanted to show you. However, we are also, I should have mentioned, there's a slight ugliness here. If I look at the syntax of this rule, for example, all of this is prefix notation. We will fix this. This is in progress as well. So calculational proofs and infix syntax are like the very next things on the agenda, but we also want to do things like, it would be really nice if you were, let's say you were doing a proof about an automaton. You could just draw the diagram of the automaton and it would have an understanding of what that was. Or if you're doing something with category theory, you could have a commutative diagram. You just do that. This sort of thing, or defining a programming language using a grammar. You just write the grammar and it generates all of the rules and all the structures that you need. It should be possible to add all these sorts of extensions for specific classes and use cases, but it can already be used in a classroom setting. You could, I know it's used in TU Dresden for a simple logic class, just doing some propositional logic and stuff. I know also there's someone in Australia who formalized Martin-Löf type theory in Holbert, which was an interesting use case for it. But writing a whole textbook would still require more features. Also, I'd like to do things like support exams. So, you could have parts of the document which can't be edited, and like users can submit their exercises to some server or something like that. But the main thing that a textbook would require would be multiple documents, being able to import other documents and stuff like that, so you could develop a library over the course of the textbook. In the paper, there's all the gory details of how we make pattern unification work for us, and other implementation and design details. Contributions are welcome. This whole thing is implemented in Haskell and compiled to JavaScript using GAC.js, which can be a pain to install, but hopefully once the WebAssembly backend for Haskell becomes more mature, we can shift over to that. All right, thanks.
All right, yeah, I think we can take a couple of questions.
So I'm completely blown away by this. This is great. I'm actually currently in a course about linear logic, and we're doing these natural deduction proofs on pen and paper just a couple months ago.
Right.
So kind of related to that, my question is, have you looked into either what features would be necessary, or if it's already possible to support the sequent calculus presentation of logics?
So yeah, I personally dislike a sequent calculus, which is why I didn't implement it. But like that's just my sort of bias. But you could support something similar with the sequent calculus, but the main thing is that sequent calculus is like more general in the sense that you have like more than one possible conclusion in a rule, as well as and you can work on either side of the sequent in a way that doesn't really work in natural deduction. So you could do something similar, but I don't think Holbert will ever support sequent calculus style presentations or sequent calculus style proof calculi, at least not directly. But as for linear logic, that's also a problem. The reason is because this is sort of assuming that your context of assumptions is structural. So any substructural logic would be tricky. You could do it by reifying the context into an explicit object and then talking about how it gets split up and stuff, but it would be a bit painful. Yeah. Yep.
I see that you're always changing the name from N to K.
That's another feature.
You can add a feature just not using it. And even if the name is bound, don't use it.
Yeah. Okay. So we're going to add a feature that if the name's already bound, it'll add a prime or something. Yeah.
So you mentioned like a diagrammatic accommodant, and you mentioned categories. Have you had any thought about diagrammatic rewriting in categories?
I don't even know what that is.
Okay, like you can sometimes like categories like this diagram, so you have like kind of like a circuit diagram, and then you can have like rewriting of these circuits.
Oh.
Is that related to proof normalization?
I'm not entirely certain where I'm coming from. But essentially, like the equations you write out in, like, let's say, a monodal category is actually like can be expressed as a circuit and vice versa. After like some.
I don't. My short answer would be I don't know enough about that.
Okay.
Yeah.
The like I say, I love the idea, right? So that's the question I know. What's the pathway to using an actual prover, right? In the same way that we design teaching languages, with maybe some thought about pathway to a real language, right, after the fact. Right? Have you thought about that with Holbert?
Not really. I would say that architecturally, this internally, it's almost exactly the same as Isabelle. So there would be a pathway, probably the easiest pathway from Holbert would be to Isabelle. The only difference being Isabelle has types, basically. The logic is exactly the same, except I removed the type system from Isabelle. Yeah, if you wanted to generally, the problem is the experience of using Holbert is quite different from the experience of using any other proof assistant. However, it still has the same video game charm. So I don't know, it's sort of like moving from a graphical programming language to a text-based programming language in a way. Yeah. I haven't thought about it much though. Yeah?
So in your presentation, the proof tree context, I see that you have the option view only. Is this kind of the default?
Yeah, that's the default.
Or is this just for resident purposes? Did you then look at how students deal with that?
So for example, the hidden one is the default one from Jensen's paper, but it defaults to new only. You can actually have all, which would have every single assumption listed in every single goal, but this just gets too wide too quickly. That's why I have this.
This is Jensen stuff.
Yeah.
Just before conclusion, right?
Oh, it's like sequent calculus, but with one conclusion.
Which is,
but Jensen's natural deduction presentation hides the assumptions.
yes.
And just gives them names.
But it's good that you have the option.
Yeah, we have the option to list all of them. But,
Okay, last question.
Yeah.
Students get good at playing video games, but you give them a blank state and then do they panic.
What do you mean?
So they get used to doing this, right?
Yeah.
Click, 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 and then exam time comes.
They have to write a proof.
Click, 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 click.
So I think that my sort of, okay, it depends on how this question is meant. If it is meant as a criticism, I would say that criticism also applies to existing courses that use proof assistants. In fact, a lot of people end up just figuring out how to convince Koch that their theorem is true, but they don't know why it is actually true. And I would say that Holbert has the edge here slightly because what you end up with once you've completed the video game is actually a readable proof in a sense, or you can convert it into a readable proof. Whereas what you end up with half the time after a long session of proving in a not traditional proof assistant is a long tactic script, which is completely incomprehensible unless you step through it piece by piece. So I think we still have the edge in that sense, but you're right that the video game aspect can actually be a distraction from understanding what's really going on. And that could cause a problem if you're then faced with a problem that you need to solve by hand, right? Yeah, I don't really have a good answer for that.
I think you just give the students a few exercises by hand during the course.
Yeah, yeah.
I mean, I think what you said about having the version that is readable at the end is definitely helpful.
Yeah.
I'm teaching this semester with my own proof assistant, which actually shares a lot of
Sassy LF.
Sassy LF. Yeah, that's right. So it seems to work out, right? That students on the exams don't have the tool and they still can write proofs.
Right. Okay.
So, but
That's
yeah, it's definitely an important thing for tools in this class to pay attention to. So we are a little past the time. We should move on to the next speaker. Thank you very much.